Great. It's always a good icebreaker to get somebody to pronounce my name. Okay, so I think it's been a long 3 or 4 days here, so what I thought I would do is to try and give you guys a little bit of the summary of the projects that we're involved in at Edinburgh, and really over the summer school you've probably learned a lot about the techniques underlying the optimal control, motion planning, for sensing, navigation. But really, if you want to try and put this together into some real concrete projects that push the boundaries of what we can do, then we have to really worry about these techniques, but also think about what is required from a perspective of deployment. So the way I'm going to try and do this is to give you a few examples of projects that we're doing, and then talk about the underlying science that enables us to do the kind of stuff that is required. So that's why the term shared autonomy comes from the fact that in many of the projects that we are involved in, it's not fully autonomous, as in robots doing things on its own. It's not fully teleoperated, but the boundary between those two things is quite blurred. So again, I don't need to motivate the crowd here, but you can see that robotics is now being applied in domains ranging from the nuclear industry to smart cities, self-driving cars, the medical industry. So the one thing that is really challenging is what's happening from where we were 10 years ago to what's happening now, where a lot of the push so far has been trying to create more and more autonomous behaviors, trying to create let robots make decisions on its own. But really I argue that in the next sort of 5 to 10 years, the real challenge is somewhere in between, where we will have to seamlessly move the slider between fully teleoperated scenarios to fully autonomous operations, and somewhere in between. And not just in a single task, but in a task, not just in multiple tasks, but even within a single task. An example can be where you have to, say, get a robot to walk through or navigate a complex environment, reach for something and grasp an object. There may be some scenarios where teleoperation of directions and paths to disambiguate between multiple options is the right thing to do. On the other hand, you want the system to automatically decide for itself what are the basic behaviors, like avoiding obstacles, maintaining balance, doing multi-contact interactions. All of those things we would like to devolve to the system rather than me having to specify all of those things. So that's really the challenge in robotics, in the next wave of robotics that we need to do. And again, a new kind of science is needed for that. So again, I've just listed here the reasons why fully autonomous behaviors, as one would have thought about in terms of a quest for doing things, is probably not going to be our end goal. We need scenarios where we want to strive for this, but still be able to deploy systems where full autonomy is not an option. And really, I don't want to repeat all that I've written here, but across domains, these are some of the domains that at Edinburgh Centre for Robotics we have more or less different amounts of work going on, but these are the challenges where full autonomy makes it hard to do. So as I said, what I'm going to do is to try to give you maybe 4 examples of projects that we work on, and try to list the underlying science that has enabled the projects. Again, I'll make these slides available. There are some references at the bottom in appropriate places where the details of the algorithms, the methodology, the core scientific elements are listed in more detail. But here I want to try and address some of the issues that we've been looking at. So, for example, there's a project on shared autonomy for remote operations, where the challenge is to run a system like this, a console which looks at from a person operating perspective, without direct line of sight, looks at a console like this, where they have to, in real time, build a map of the environment, local map of the world, create affordances in terms of which arms to use for grasping which objects, and along the way do things like clearing debris while doing path planning. So again, multiple elements involved there. Obviously high-level motion planning. Then there's some work on using what we call capability maps or dynamic road maps, in this case to understand what is the best position for the base of the robots to stay, for two reasons. One, we want to improve robustness in terms of reachability, but we also want to improve or optimize positions. So using that, and then in combination with that, using things like real-time sensing for understanding affordances. And again, there are some high-level inputs that the humans give in this case, which include things like which is the object you want to grasp and where do you want to put it. So those sort of high-level inputs still come in. So if you think about trying to create a full system like this, what are the elements that you require? What are some of the elements that you require? You've seen a lot of work from Oxford, including Morris's work on taking multiple sensors and creating a whole body map of the world around it to localize and create a sense out of it. We've done some work on real-time sensing. So for example, going from very raw information like this, so RGBD sensors, raw information like this, to affordances, and then finally motion tracking in real time. So for example, going from this kind of a image to doing model-based tracking. So model-based tracking in the presence of occlusion, in the presence of clutter, in the presence of a significant out-of-depth camera images. So and these are just one of the capabilities in terms of tracking that's required, and with the real-time nature of tracking that's required to make some of these behaviors happen. Again, here we are not dealing with contacts yet, so anything which responds to forces, contacts are ignored. But these are the core capabilities that we require. And again, some references can be some work that points to the underlying code base for that. The second bit, and again, some of you would have heard about it through Vlad and Wolf and others here. There's a framework that we're developing for such an integrated platform, which involves taking a problem of motion planning with sensing into account, but breaking that up into various bits and pieces. Breaking it up into a bunch of inputs, a bunch of outputs that you want, but also creating some very distinct ways of defining problems, both in terms of the techniques that we use to solve it, in terms of motion planners, as well as defining the problem. So very explicitly forcing you to define what is the problem that you want to tackle. Is it what are the kinds of end maps that you want to work with? What are the kinds of task maps you want to work with? What is the environment you want to work with? And the whole point of doing this, or the whole point of forcing you to do this, is so that you're not comparing apples and oranges when you do comparisons of algorithms. So by using something like this, we can take existing solvers like OMPL-based solvers, but also we are able to benchmark and create, really understand where the limitations, where the bottlenecks are, rather than saying, I use this platform and this algorithm in this setting, and hey, we don't know where the differences come from. So again, we've actually tried and deployed some of these planning frameworks in some projects. I'll talk a little bit about the Orca Hub, but here's a quick couple of videos of a mobile-based platform that we've developed at Edinburgh. it's a spin-out called Robotics, where you've deployed exactly this motion planning algorithms to go and work in fairly complex environments, in deployment of sensors, in fairly unstructured environments, doing sensor placements there. Again, the core of the mobility of the platform, the core of what kind of sensing, what kind of motion planning required, all comes through the Exotica motion planning framework for deployment. So again, this concept of sharing autonomy between what a robot can achieve at a high level and what needs to be deployed on the platform can be used in domains ranging from nuclear decommissioning to collaborative manufacturing, but also we've got one of the partners in the MEMO project, which is Costain, and one of the many challenges they have is in deploying heavy machinery like these in underground digs. One of the areas we're looking at is cement spraying. How do you automate some of those elements, semi-automate, or again shared autonomy aspects in cement spraying settings. So the second project I want to briefly allude to is this project called the Orca Hub, which stands for Offshore Robotics for Certification of Assets. It's again a UK national project, which is we've got a few people here who are part of this consortium, including Oxford. And again, the whole idea is to do the full stack from sensing, navigation, planning, certification, and verification of some of the motion plans. So the whole stack, not just saying we get robots to do something, and we don't want robots to be the weak link in any of these certification assets. So we've got, for example, we've got Lloyd's Registers as one of the partners. So they make sure that we create motion plans, we create algorithms that are verifiable and certifiable. So, and you've seen this video already probably a couple of years ago. You've seen probably much more latest videos from Marco yesterday. But the whole point is trying to get mobility on complex terrains like this for deployment of various sensors, both for sensing the environment. Well, two things. One, we want robots to sense its own state and environment, but also we want to place active sensors in these places to get state estimation. So if you think about, again, the underlying challenges, besides the usual dynamics, besides the usual sensing challenges and state estimation challenges, in complex environments, one of the challenges is how do we represent targets, how do we represent goals? And some work that we've been doing in this domain since the past 5-6 years is in the use of topology as methods for representing targets. So whenever we have the environment to deal with, then the goals that we need to achieve with robots can be fairly complex if we do this in Euclidean space. But if we use slightly, if you think about what are alternate abstract spaces that we can use to represent our goals, I've listed a few. Again, I don't want to go into the details, but then if you use some of these abstract topological constructs, then various things become easy. So for example, let me give you a very simplistic video, a look into getting a robot arm to reach into this box. So we can do this in any number of ways, but if we now specify the goal target of reaching into this box as maintaining a particular topology, then when the box moves, the concept of what is inside and outside moves with the box, and because of that you can do efficient replanning very quickly by providing constructs or gradients in this topological space. So this is just one example of using topology and gradients in this space to do very fast replanning. Yes?
Excuse me, can you comment better? What do you mean for topology? Like keeping the distance from the box?
It's not the distance. So in this case, topology for this particular example, there are some interaction mesh-based relational descriptors which say that only thing you need to maintain is that the arm has to be inside the box. So when the topology changes when the arm goes from inside to the outside. But as long as the arm is inside the box, the topology stays the same, irrespective of the distance from the boundary. So in a way, we are saying that it doesn't matter whether it is close to the boundary or not, as long as the arm is inside the box, as long as that topology is maintained, that's enough. From a robustness point of view, that may not be the best thing to do, but indeed that helps us generalize concepts in various ways. We can have additional constraints for introducing robustness. There are other things like harmonic electric fields and relational tangent planes which solve different problems. For grasping, we've used harmonic electric fields to specify targets which are non-intersecting, which have some nice properties that it doesn't get stuck into local minima for particular kinds of shapes. And we've done similar things on flexible objects. So these are just examples of topology used for working with high degrees of freedom, highly complex environments. And again, some of the examples where this has been deployed or we're working with deployment is examples like snake robots. So for example, this is with OC Robotics. So planning in such environments with high degrees of freedom is a challenge if we do this in conventional Euclidean spaces. But on the other hand, if we do this using this constructive topology, then planning in such spaces becomes less challenging. It's still sensing and calibration is a hard problem, but doing this in real time becomes easier in these constructs. Okay, so one other thing I want to mention within this framework, even if you have the best sensing, even if you have the best state estimation, we still have uncertainty in the world. So to be able to deal with uncertainty, we can do many things, and one of the things is to work with passive compliant mechanisms. Again, for people who have not worked with compliant systems, effectively it's like attaching a spring in between an actuator and an end effector, and the springs can be various. It can be fixed stiffness springs, or you can have a scenario where you have the ability to modulate the stiffness of the spring. So there are various mechanisms in place to do that. So why would you like to modulate stiffness? This is basically if you know that from a particular task's perspective, you want to, for example, reach very, very accurately at the end point, but during the motion I want to be rather compliant and give in if it hits an obstacle. Or if I want to be energy efficient during the initial phase, but I want to be very accurate at a goal point. In those kind of scenarios, we want to be able to modulate stiffness. So that is the whole principle of variable stiffness actuation systems. And what we've done is, this is not new. Many people have worked on this variable stiffness actuation systems. We've built a few systems in Edinburgh. For example, the biped locomotion, which is capable of varying stiffness and damping. But what has been one of our key contributions has been taking an algorithmic view on finding the efficient ways of modulating spatially and temporally stiffness on a variable stiffness actuator. So again, fundamentally speaking, it is nothing but having a system capable of modulating not just positions, but also stiffness by adjusting your input. Then you have it's your standard optimal control formulation where you have a model of the system which includes the modulation of the stiffness. Then you have an objective that you want to optimize. For example, if you want an arm to throw a very far distance, then you want to modulate. You want to minimize this where you minimize the negative of the distance or maximize distance. and then you minimize the energy consumption, and then you use your optimal control solution to give you your solution. Now the point is, the solution now includes not only the spatial modulation of each of the motors that control the positions and torques, but also modulates the stiffness. Okay, but that's not new. But the good news is that this whole framework of optimal control formulation can now be reformulated as a Bayesian optimization framework. So again, this is work from about 4 or 5 years ago now, which looks at taking, for example, a Markov decision process, and now formulating some of the outputs of the Markov decision process as functions that essentially tell you whether what is the nature of the success that you have achieved based on some what we call indicator variables. So once we do that, once we formulate that, it turns out that the solution for the optimal control that we typically get by using this and solving it using your favorite optimal control algorithm, could be DDP, could be ILQG, could be whatever else, can be rewritten as a Bayesian optimization framework, and this is work that we've shown direct equivalence, and for more details, that's the reference. So, and the advantage of that is now, if you now combine those two things, one is the abstraction that I talked about. You know, it could be using the relational descriptors, or it could be using some other ways of intermediate representations. If you use those abstract representations, and then you, and that can be those x0, x1, x2, those are the abstract representations that you can observe, and then you represent the Markov decision chain, which captures the optimality criterion as shown in this transition probability. So state dynamics cost function, which captures the optimality function. Then we can exploit the standard algorithms from the field of variational inference to solve these techniques. So to solve these problems. So if you look at the approximate inference control algorithm, or the ICO algorithm, that's again one of the tools, sub-tools for solving approximate inference that is built into the Exotica platform that exactly uses this formulation. So what comes out of this is not just the so because I formulated the dynamics which includes the stiffness modulation, I get not just positions and torques, but I also get the stiffness modulation, the optimal stiffness modulation for the gate or for a particular task. So here's an example of using this stiffness modulation. So actually, if you have the voice, it's a lot more impressive. So this is two-link robot arm and the ability to modulate stiffness at every joint. And what we've done is we've optimized the stiffness using this algorithm. And again, I don't have the time to go into the details, but the whole idea is individually each of the motors are not powerful, but by giving it the ability to pump energy into the system, store energy into the springs, it automatically finds a strategy for making movements that stores energy into the system, modulates the stiffness of the joints, and maximizes distance thrown. Again, we have compared two things here. We have compared one scenario where there are fixed springs. We don't allow the spring to change the stiffness. Already doing that allows better performance through pumping energy into the system. So that is just by having springs and the ability to store energy maximizes distance. But now having the ability to modulate the stiffness in a spatiotemporal fashion optimizes on that. So that's what we've done for this low dimensional system. We have limited success on, and we've done something on the DLR, a Hassie arm, again a long time ago. We have not done enough on this, but would be great to try some of these things on some other variable impedance modulation platforms. So at the moment, we find both the Animal and the Valkyrie platforms, they have series elastic actuators. We don't have the ability to modulate stiffness on it, but there are other platforms which we could potentially try this. This is some work so the similar strand of work can be now deployed on modulating stiffness and contact forces on Animal. So for example, some work by Mike Mystery's group on, and you've probably seen some of this work, especially if you look at the latest ICRA work that's coming out of Mike's group, is looking at hierarchical controllers for legged systems subject to external disturbances. Here the idea is to minimize external disturbances by modulating stiffness. So these are examples of modulating. I thought I had, yeah. So again, this is work from Mike's group on using multiple arms and adjusting stiffness properties. I think Ozzy is there somewhere in the crowd. He can tell you more about that work on using multiple contacts to adjust both for this fixed fixed weight platform, but also adjusting using some learning mechanism, which I'm going to next get to. Okay, so this work, we've now, this concept of adjusting stiffness and modulation and collaborating, we've also done, we've extended this in collaboration with the Honda Research Institute recently on creating formalisms for both, for dyadic collaboration, where you want to, it's a little bit like a mixed integer solving problem, where you're not only optimizing for continuous trajectories, but we also want to optimize for positions where you do the grasping. So, we've been looking at some work on dyadic collaborations for manipulation for hybrid trajectory optimization, where the idea is we want to optimize, and you'll see a sort of animation in a bit, where we want to optimize not just the forces and the trajectories, but also the positions of the grasp holds. And again, there are various elements to it. If you are a follower or a slave, or if you are a leader, so you have to be able to judge the opponent's policy. You want to model opponent policy in addition to optimizing for continuous and contact positions and continuous motions. So there are many levels to it. One is obviously having a whole framework for establishing opponent policy and then incorporating that policy into an optimization framework that is hybrid. Hybrid because it's doing both discrete changes in location of contacts as well as optimizing for forces and positions. Again, some more details in paper down below. And where do we're sort of working with various application domains, including some work with some aircraft industry people, some people in Comac in China, for example. Okay, so the other project you probably know of is the Valkyrie project at Edinburgh. Again, this is part of a bigger mission in terms of creating capabilities on humanoid platforms for pre-deployment missions to Mars. Again, we are looking at a very small part of the puzzle in terms of doing whole body motion planning in complex and cluttered environments. So again, we've done a bunch of work on reachability maps and capabilities for both local manipulation and close contact interaction with humanoid platforms. So here's a quick summary video of some of the work that involves, for example, walking and grasping this box, but now what happens is we change what's around the table. So, for example, in this case, the robot has to walk up, sense that there is an obstacle, change its location for standing before reaching into it. So effectively, finding the most optimal stance in the presence of obstacles that are not being there before, and sort of planning that in order to grasp it and manipulate and control. So this is again part of the whole system of sensing, local manipulation in the presence of unstructured obstacles. So the good news is that, and again this is combining work on sensing, locomotion, local manipulation, that will basically enable us to get to a stage where we can start looking into problems where, for example, we've got a really complex terrain, then we can use this platform as a way of finding the right motion plan, not just the end effector plan, but also the full body stance location, the optimal stance location for various things like efficiency of motion, stability, in order to do grasping in complex settings. So this is again some preliminary work we have on working on fairly complex terrain. Again, Henry is here. You can ask him more on that work. One of the bits that we are trying more and more to incorporate into this work is some work on learning to predict and adapt from behaviors. I'll try to be rather quick with this because this is rather old work, but the fundamentals are still the same. This is work that we've done where we're using data from learning, and again at EDF here, Sylvain does a lot of that work, using the data to learn, in this case, the inverse dynamics of the arm, and then later on here, using data to learn the torque dynamics of the pole that you're trying to control. So in a way, you're using a data-driven way of finding policies that will enable us to use these things when things change. If I now take out the pole, the rubber ball on top of the pole and change the dynamics of the pole, I can use data-driven techniques to adapt the inverse dynamics to learn this on the fly. So that's just thinking of it like just learning inverse dynamics, right? But we can now do this in a much more comprehensive setting. We can now put this within the optimal control loop, so to say. So we've done some preliminary work. Andrea, who's now at IIT, has led that work during her PhD, where instead of having a sort of open loop system where you've got tasks, cost functions, some existing dynamics, optimal control, and then you do this kind of finding the best optimal control solutions to do it, we can now complete the loop by looking at what happens, collecting the data, learning an internal model, not just the model but also the uncertainty, and then put that into the optimal control framework to deal with both uncertainty as well as potential change of policies based on uncertainty to go with what you really care about. So this is some work that we've done on relatively low dimensional systems. We've done some stuff on brachiation. Again, I don't have the time to show you some of the details, but again, so brachiation using varying loads. We've done some stuff where we've done optimal control and learning in the loop. But again, scalability is still a big issue in these kind of cases, so it's something to think about. Okay, I'm going to skip this. I don't want to embarrass Vlad here with. Maybe I should. Okay, so this is Vlad in his fine kit. So this is we've kind of tried to combine various elements where we've done some online motion planning, replanning in the null space of the target while maintaining. So this is constraint-based replanning, as well as some aspects of compliant manipulation. And so all of these things. And as you can see, it's a very Scottish robot. It's very possessive of its drinks, and so and finally, we also some work on shared autonomy in healthcare, where we've done significant work on upper limb prosthesis in collaboration with Touch Bionics, and there's some recent work with some exoskeletons from Pisa, from Santa Anna's exoskeleton. So here's some work on prosthetic amputee testing that we've done on using predictive techniques for figuring out or pre-shaping the grasp on amputees so that people can do what we call pre-grasp classification. This is where shared autonomy, again, it's the same theme of shared autonomy coming together, because we are devolving some of the pre-shaping of the grasp to the autonomy elements, and the open and close is still being controlled by the people who are actually varying the EMG sensors. So the whole idea behind it is not to reduce the cognitive load on the person who is operating it by taking out as much of the decision making out of the people's hands, but still leave the critical aspects of when to grasp and open in the control of the people who are doing it. And then finally, this is some work, again this sort of nicely shows the platform that we have for exoskeleton testing at Edinburgh. It's going to be of quite interest to Wondercraft, because I know that you guys have a very similar platform. So the Motec treadmill with the whole sort of force plates and perturbation capabilities with Wycon. But this is the Pisa exoskeleton that we've been looking at for assistance in rehabilitation testing. The whole point we are focusing on here is a closed loop control, or essentially looking at how we can look at gait metrics. So the first thing was looking at identifying what are optimal gait metrics that we want to focus on, because kinematics alone, dynamics alone, force information alone, just the butterfly gait alone, we found that it's not enough. But Daniel has worked on a bunch of metrics that we found are in combination are good indicators of stability of gait and what we call normal gait. And now the next step for us is to close the loop and close the loop in terms of the controllers in order to apply the right assistance in real time by detecting phase and the forces so that we are able to correct the gait towards the right setting. So that's all I have to talk in terms of some of the projects that we're doing. So it gives you a nice sort of fly-by view of the kinds of things that we're looking at. Finally, I want to end by showing you a little bit of what of the centre that we have at Edinburgh. Most of you have been there. Others who have not been there are welcome to come and visit us. So I direct the Edinburgh Centre for Robotics with David Lane and Harriet Watt, and one of the challenges, one of the things we're looking at is how we can take the innovation from the labs that we do to market through asset skills and clusters. So assets meaning we've got world-class equipment, humanoids, wheeled robots, quadrupeds. Skills refers to the Centre for Doctoral Training. So we have a PhD program that we got some good news recently. It's still under embargo. I think it's going to be released on Monday, so please keep it to yourself. We've got a renewal of our CDT, Centre for Doctoral Training in Robotics and Autonomous Systems, and we work very closely with government for legislation. So that's the CDT, Centre for Doctoral Training. This is what we call the Robotarium, or the equipment that we work with. But indeed, one of the in doing all this science, in doing all this research, we do have to worry about other aspects because a lot of you're embarking on your career in robotics in this area. So in doing all the good science, I think we should also think about all of these things. We may not do this ourselves, but we need to collaborate with people who worry about these things. I know that we look at some of the learning systems, the challenges of learning systems. We also do some stuff in this area of when and how to transfer control with robotic platforms. But we've also started looking through the Alan Turing Institute at some of the other aspects in terms of verifiability, explainability, and things like, if you look at Lyapunov stability of a particular control system, how does that translate to deployment on robotic platforms? So those are the kind of things that we've started looking at, and I've just started a new role in Alan Turing Institute as co-program director of AI, and one of the things that we're doing is to look at a scientific program of data-driven AI and research that addresses the challenges arising from and towards deployment of robotic systems. So that's our sort of mission at the Alan Turing Institute, at least the robotics side of things, and I'm looking at 3 programs, 3 research strands that we're supporting at the Alan Turing Institute, and if any of you are interested in any of these things, please come talk to me. So, scalable algorithms under constraints, how do we use it for real systems, how do we push algorithms to scale, methods for efficient multi-agent computations. This includes intention detection and movement prediction of agents and adversarial scenarios, and how do we deal with the complexity of multi-agent interaction in robotic systems. So multi-contact is just one aspect of that kind of interaction. And finally, of course, verifiable, robust, and explainable decision making. So how to give people confidence that the systems that we're building will not fail, or has some guarantees. So these are the kind of interesting challenges that we have to address. So to be able to do that at the new base center in Edinburgh, we've been looking at what we call living labs. So we've been looking at robots for extreme environments. I've given you some examples of projects that we work on. So different kind of platforms, so robots for extreme environments, but more interestingly, we've also started some new work on robots in healthcare and assisted living, so mock-ups for smart homes, exoskeleton and prosthetic devices, hospital and surgery mock-ups. So I don't do that myself. One of my colleagues, Ram Ramamurthy, is leading a project on this kind of robots as assistants in surgical systems. But all of them have to deal with this issue of safe and ethical AI. And this is the new base center. For those of you who haven't visited us in the last couple of months, please come and visit us. Some of our facilities have moved into this nice building with 2 floors of new robotic facilities. Trying to push that. So it's a good space to work in. And we're quite lucky to have that space. So thank you very much. I hope you got a general idea of the kind of science that we do and the application domains we work in. Please talk to me or any of the guys from Edinburgh if you want to know more about that system. And hopefully those of you who are staying, hopefully we have a good review meeting. And those of you who are headed back home after summer school, safe journey. Bon voyage. Thank you. So I'm happy to take any burning questions if there are any generically, but otherwise I think we are running a bit short of time for discussion with the PIs on the review meeting itself. So, thank you.